Welcome back. In previous sections, we focused upon conduction in walls. In topic 6, we study conduction in a fan. What is a fan? A fan is an extended object from a base surface, and it is subject to convection on both side surface and tip surface. What an actual fan looks like? It could be a straight fan as the one on the outside of radiator, or it could be an annular fan as the one on the outside of the tube, or it could be a pin fan with circular cross-section area as the one on the top of the tube set. Then, what is the heat transfer role that a fan can play? First, our system is a pin fan. The base has a temperature Tb, the fan has the length L, diameter D, thermal conductivity K. Along the length is the X direction, and the fan is subject to the convection with moving fluid at temperature T infinity and heat transfer coefficient H. For such a fan system, the heat transfer modes are: within the fan, there's a conduction heat flow. On the boundary of the fan, there's a convection from the side surface and the tip surface of the fan. Third, now you understood that fan's role is to deliver the heat transfer through convection from both side and tip surfaces. Then the question is, the heat delivered by fan QF can be calculated by the convection heat equation? The answer is no, due to the fan temperature change from the base to the tip. Fourth, what we can do is to solve the secondary ODE with one boundary condition at the base and the other conditions at the tip, so that we can get the mathematical equation for the temperature distribution along the fan length. Then we do the integral to get the math equation for the heat delivered by the fan. Then, what are the equations looking like? In this table, under the condition that the tip has the convection, this equation provides the temperature distribution along the fan. This image gives you an idea how the temperature reduced over the length. This equation then provides the calculation expression for the heat delivered by the entire fan QF. In this equation, the cosine H, sin H are hyperfunctions. This table provides the value for those hyperfunctions. In these two equations, M and capital M is defined here. First of all, P is the parameter. For a pin fin, it is pi d. For straight fin, it is 2 times W plus H. Second, AC is the cross-section area at the tip. If it is a pin fin, then AC is pi d squared divided by 4. Otherwise, if it is straight fin, the AC is width times the height. Third, the lowercase m is a combination of the fin variable, heat transfer coefficient, parameter, thermal conductivity, cross-section area in the unit of 1/meter. The capital M in the unit of watt is a combination of fin variable as well. This is temperature difference, coefficient, parameter, conductivity, and cross-section area. Following is an example 3-7. This is for students to practice so that they get familiar with the fin equations. We will continue our lecture. As we have discussed, when we try to get the math equation for the heat rate by the fan, QF, we need to solve the ODE with tip boundary condition. The question is, can we have a different tip condition? The answer is yes. The first tip condition is case A, convection. That is, there's a convection between the tip solid surface and moving fluid. The second tip condition is case B, adiabatic. That is, there's an insulation layer at the tip. As a result, there's no heat flow in or out, even though it's still subject to convection. The third tip condition is case C, fixed temperature. That is, the temperature at the tip is fixed. The last tip condition is case D, an infinite long fin. That is, since the fin is so long, the tip temperature is really close to the temperature of the moving fluid. That's the reason why in the winter your nose tip is always colder. Furthermore, we provide a criterion so that we can judge by comparing M times L, the length of the fin, whether it is greater than 2.65. It is, then it is an infinite long fin. So we do have 4 different tip conditions. The question then would be which tip condition to use for fin problem. Here is the strategy. Assume it is a tip fin problem. You start with assuming the case A, convection for tip condition. Then you check the problem whether there's an insulation layer at the tip. If yes, then it is case B, adiabatic tip condition. Otherwise, you continue to check whether at the tip the temperature is fixed. If yes, then it's case C, fixed temperature tip condition. Otherwise, you compare ML with 2.65 If it's greater than, it is case D, infinite long fin tip condition. Otherwise, you go back to case A, convection tip condition. Next, based upon the 4 different tip conditions, we have 4 different equations for the temperature distribution along the fin, the 4 different equations for the heat delivered by the entire fin. This is the table for hyperfunction value. Once we have fin equations, we wondered how to evaluate the fin performance, since the fin is used to increase the heat transfer effect. There are 2 fin performance parameters. The first is the fin effectiveness, epsilon F, which is the ratio of 2 heat transfer rate. The first one is the convection rate between the surface area AB with the moving fluid without fin. The other rate is the convection through or from the tip surface at the same area as AB and from the added side fin area. You can imagine the fin effectiveness is supposed to be greater than 1. As a result, we only recommend using fin under the condition that the effectiveness greater than 2 to overcome the cost when the fin is stalled. The second fin performance variable is fin efficiency at F, which is also the ratio of 2 heat transfer rate. The first heat transfer rate is convection from the side and the tip surfaces for our actual fin. That is, the temperature of the fin decrease along the fin length. The other heat transfer rate is the convection from both side and the tip surfaces for ideal fin. That is, the temperature of the fin from the base to the tip remain the maximum. You can imagine the fin efficiency is supposed to be less than 1. Now, we're going to do the example 3-8 to apply all the knowledge we learned before. As you can see, there's an experimental device producing excess heat, and it is passively cooled by a copper pin fin. So we know this is a fin problem, and it's a pin fin. The base is the wall at the temperature TB. The fin has the length L, thermal conductivity K, diameter D, and it is subject to the convection with the flow at T infinity and H. What we need to find out is the temperature of the fin at location X and heat rate, effectiveness, and efficiency. Since we know it is a fin problem rather than a wall problem, let's get ML value first. Since it is a pin fin, we calculate cross-section area at the tip which is pi d squared divided by 4. Then we calculate parameter, which is pi d. Next, we can calculate the side surface area, which is pi dl. Then we can calculate the lowercase m, which is heat transfer coefficient, time parameter, time thermal conductivity, time cross-section area to get m value. Then we can calculate ml. This is m, this is the length. So we get a value is greater than 2.65. The second step is to determine the tip condition. We start with case A, convection at the tip. Then we check there is no insulation at the tip. Then we move along, check whether the tip temperature is fixed. It's not. Then we'll move to next case D, infinitely long fin, since ml is greater than 2.65, so the tip condition is a infinite long fin. Once we know the tip condition, we can go to the full actually it's 8 equation table to select the temperature distribution under the tip condition of infinite long fin. Then plug into numbers. This is the temperature we're looking for at this location. This is the flow temperature. This is the base temperature, and this is the exponential m value. This is the location value. Then we solve for the temperature, which is 19.7. It's pretty close to the 95, and it makes sense. Since we know it is the infinite long fin tip, we can select the math equation for the heat delivered by the fin. Then plug into the numbers, temperature difference, H parameter, thermal conductivity, and cross-section area to get heat rate by the fan. Next, we can measure the fan performance from the definition for the fan effectiveness. We plug into the number. So since we already calculate the QF, we plug into here. So this is the H AB, which is the same as the tip area, then a temperature difference, so we get a big value for effectiveness. Then according to the definition for the efficiency, we can plug into the number. We know the QF, H. The EF is the summation of side surface and tip surface. Then a temperature difference, we get a relatively low efficiency. At this point, we covered topic 6. We define what fan is and clearly showed the purpose to use fan is to increase heat transfer effect by increasing the contact surface with the moving fluid. Then we can use the effectiveness and efficiency to measure the fan performance. When we solve the fan problem, we need to distinguish it from a wall. Once it is a fan problem, you need to determine the tip condition. There are 4 options. Then you select the proper equation for the unknowns from the table. At this point, we finished chapter 3. We have a beautiful summary and outcome about concept, verbal skills, equations, and then we end chapter 3.